Thank you. Thank you, Amy, for the nice introduction. Good morning. My name is Peter Kyvergya. I'm Director of Analytics for the Iowa Soybean Station. And for me, it was a very short drive. I live here in Ames. So again, thanks for coming. The Iowa Soybean Station, it's a farmer-owned, not-for-profit entity, which is located in Ankeny. It deals with a lot of different issues related to soybean. And the Soybean Association has a research department, which comprises of 3 different teams. The first team, it's called On-Farm Network. This team works and deals with different issues and conducts on-farm trials related to agronomic problems. The second team, called Environmental Programming Services. This team deals with environmental issues, specifically doing a lot of water monitoring, environmental assessment, and also all kind of different watershed planning and assessment. And the last team, which I represent here today, it's called Analytics, which we help to both of these teams collect data, analyze data, summarize data. And we also conduct research with industry and university, and specifically here with Iowa State, the Iowa Soybean Center, the agronomy department, plant pathology, statistics, and so on, in project focus on precision agriculture, remote sensing, and modeling. I assume most of you are familiar with precision agriculture technologies, which became available about 20 years ago. Those are simple GPS system, remote sense, and so on. But a lot of time recently, people talk about so-called digital agriculture. And I assume some of you are dealing with this system where a lot of data coming from different systems, big data, and all people trying to analyze this data and trying to make better decisions for agronomic and different purposes. But what happened about 20, 15 years ago, that these technologies allows us to conduct so-called on-farm research, on-farm trials, agronomic trials. So here at Iowa Soybean Station, we usually work with about, for agronomic purpose, we use this with about 300 farmers. So you can imagine that we have 300 graduate students across the state. So each of these students has his or her own project research. The only difference between you and them that they don't need to write the dissertation, right? But so we work with many farmers. They use these technologies. It's not necessary to have all of these technologies, maybe the basic like yield monitor and some of the sensing technologies. But the key is that we can collect this data, analyze this data, summarize the data, and make some decision. And I'll show you some examples later. So here's the example how these technologies allows us to scale these small plots, which I assume most of you are doing, especially if you're genetics and plant breeding, and scale to field scale research. And this is this example of one of the on-farm strip trials. These are replicated strips specifically focused on fungicides. So again, these technologies allowed us to scale small research to on-farm and complement both small plots or small plot complement on-farm research. We do a lot of communication in our office related to on-farm research. And here in the room is Ali Arp. Do you want to raise your hand? Ali, she's a communication specialist with Iowa Soybean Station, and she helps us to communicate this idea and messages. So for example, two years ago, we published this booklet, which allows farmers to teach farmers and educate how to do correctly these on-farm trials. We also do a lot of communication focused in the American Society of Agronomy. And just recently, we developed the book chapter, which has a name On-Farm Replicated Strip Trials. It's a book chapter for undergraduate students here in US. And the book was edited by University of Missouri and South Dakota. And it's going to be published online this winter. So again, we do a lot of communication outreach as well about this topic. So here's a small example of this just simple on-farm trial. Maybe 2 treatments, maybe 3 treatments. I'm not sure this works. Yeah, it works. Maybe 2 or 3 treatments, and usually at least 20 acres. It could be anything from nutrients, both corn and soybean, nutrients, plant protections, different system, disease, and so on. cover crop, tillage, and so on. You notice that we also report some of the basic yield for experimental units, provide some basic statistic, and all management information. Something unique about this data we collect with farmers that they all available online. Everything which goes through our cleaning system, which is about 90% of all of the trials, they are posted online. So we developed this specific so-called database of online reports. And you can Google by corn, soybean, by different projects, and you can look at this data online. So everything is available. Specifically, none of these data online have a farmer's name or spatial locations. So today my job is to show some of these three examples, how we utilize these precision technologies in different projects and handling different agronomic issues. One of the examples is focused on how we combine this data across the state, and we develop decision tool. Probably you're familiar that a couple years ago, actually 10 years ago, in Iowa, there were a lot of discussion about soybean rust. And farmers started applying fungicide. But the question is, should they apply everywhere? And where and when they should apply? So this project was conducted with farmers, with industry partners too, and we collected about 300 trials, 300 locations for these years from 2005 through 2009. And then we analyzed the data with aerial imagery, remote sensing, management, and so on, weather, and trying to figure out where farmers should apply fungicide. So for example, when you look at all this data, it was very clear that this specific fungicide called Headline, that it looks like the yield response to the foliar fungicide was slightly higher with the higher rainfall in spring, which is from from March through May. So you can see these effects. And the question was why. But farmers always are asking, okay, we know we have to apply fungicide, but the problem is every time they go to the local co-op, they would get different price for the fungicide, for the application cost. They wanted us to develop some kind of big table which would tell them where to apply fungicide. So we thought about this idea, and then we came up with so-called online calculator. That calculator was developed, and we look at all of this data. We expressed these responses as probability. So we developed very simple decision support system as a calculator, and the farmer or user can input soybean price, the fungicide cost, application cost, and also make adjustment for the rainfall. And this calculator would spit these numbers, specifically like break-even yield response, the probability of exceeding the break-even cost, the average profit, the range in profit. So it was a big blast. Farmers like it, as well as university people and industry. So at least it gave them some ideas where to apply fungicide and where to not, based on this real data collected from farms and all of this economic analysis. The problem with this type of data that after a couple years, because of changes in chemistry, the calculator almost became useless now. But again, it was the first example where we could combine this data and develop this very simple decision tool for farmers. The second example, you're probably aware that many farmers use yield monitors, and a lot of time they would look at the yield maps and never use it again. They can print these maps, and they can stay on the shelf, being dusted, and that's it. So a couple years ago, we, using some of the analytical tools, we decided to look at some of the yield maps and develop the system which allows us to map profit in the space. So of course, we can use profitability from each year, specific to farms or across the state, and map this profit in high resolution maps, and then do an analysis. For this purpose, we use one of the tools developed here, actually named by one of the company called XSolver, Profit Management Zone. We use this tool as a reporting mechanism. So we developed these profitability maps for a bunch of fields. And you're probably aware that farmers plant corn and soybean, and profitability would be changed depending on the yield, prices, and so on. But the question is, what's besides prices and economics and yield affect profitability. Is it management? Is it weather? Is it soil? And so on. So this is the example which we look at this data. We can look at the mean profit. So the green color means higher profit. The red color means lower profit. So you can, the return on investment, which is slightly different spin. It tells you how much money you get for each dollar invested in cross production, like this here. And of course, we look at the standard deviation across many years, like here. And again, the large standard deviation is red color and the green color is low. So definitely we can look at both the average numbers and the variability. We use our farmers who collected this data. It's about 150 fields. Many of these fields have data at least from 4, 5, 6 years. So that's a lot of data. Usually this data would not fit in usual spreadsheet file, a lot of data. And then we look at the different parts of the state. You notice that some of this from the central Iowa, Des Moines lobe, some of them from northeastern Iowa. So specifically for north central Iowa, we wanted to look what's the effect of the pothole areas on the profitability, within field profitability. And you're probably aware that central Iowa has this specific area called potholes. These are remnants of glaciation, which came 12,000 years ago from Canada. And they're extremely poor drain. Although some of this area drain now, they still can be seen on the aerial imagery like you can see here. There are a lot of these potholes. And if you fly here during summer, you can see them quite easily. But the question is, what's the effect of these potholes on the profitability? So we look at all of these spatial data, which usually 10 by 10 meters, across all of these fields for central Iowa. And then we developed a special system. So we look at different crops, soybean, corn after soybean, corn after corn. Of course, we look at the whole system, not just the soybean per se. And then we divided this data into two parts, wet spring and the normal spring. The wet spring, usually it's when we get about more than 12 inches of rainfall from March through May. And the normal spring, it's usually less than 12 or 10. So you can see that these are profitability, these are distribution curves, cumulative distribution curves for profit per acre for wet spring right here and a normal spring. So you can see for corn first that there is a big gap. So what's happening on average, given everything is constant, the profitability in wet spring is definitely lower. Also, you can see the profitability for the potholes is also lower, and lower a lot, probably about $100 per acre, which is a lot. Now, if you go up, if you look at corn after soybean, it's the same picture, but look at the soybean. You see this curve, the gap between this curve is much smaller. You also notice that there is effect of potholes. The potholes are almost always have a negative profit in some sense because a lot of time we have to replant, we have to lose yield. But the question is why these curves are tied together. Any ideas? Why soybean? Of course, you see that soybean has a less profit than corn on average, but the variability, the noise in profit is less. Yep, good idea. Yeah, it's planted later, right. So it allows to avoid this problematic time when it's planted later, especially in early May and in April. So the question is, how does the rain affect on profitability across all of these fields? We look at and these are, again, I have a soybean on top, corn after soybean, corn after corn. I have a May rainfall here. And these are a median profit for each of these fields. So there are a bunch of different fields. You see that there is no correlation between profitability for soybean and May rainfall, none. But look at the corn. So as we get more rainfall in May, definitely we either lose yield, lose nitrogen, and something else. There is a negative correlation between profitability and rainfall. The same issue for June rainfall. Actually, all of these three categories have a negative correlation with June rainfall. But you may notice that the slope for corn is much lower than for soybean. So anyway, it's a illustration how we can use these analytical tools and do this type of analysis with all these large, big data collected by farmers. Of course, I want to now move from central Iowa from northeast to the northeast Iowa. In northeast Iowa, well, before that, Farmers like to talk about ROI, which is return on investment. And if you look at this data, that return on investment was always lower for potholes, on average 10%. If you look at this data from 2006 through 2014. In fact, in each year, the ROI for pothole was lower compared to upland except 2012. The question is why? Do you remember 2012? Drought, yep, extremely drought. So only in drought years, potholes would outperform in terms of ROI. So let's move to the northeast Iowa. At the same type of analysis, we have a lot of data. These are spatial profitability data from these maps and data supplied by farmers. But now the picture is different. Now we want to look at the drainage. We have excessive drainage, well drainage, and poor drainage. Look at the soybean here. Again, these are profitability curve. It's in dollars per acre. Looks like when the drainage, the soil drainage is excessive, we always have a negative profit. Why? The difference between northeast and central Iowa, it's because in some of this area actually sandy. And what's happening in sandy areas, we don't have enough moisture to, yep, pretty dry. Corn, it's the same picture, but it's a less clear relationship. So again, that's what we do. So this is an example of how we can combine this data using these new analytical tools and do this big data analysis. For the rainfall, of course, if you look at spring rainfall for northeastern Iowa, well, there is no relationship, except maybe for corn, after corn. But look at the July rainfall. If you get more rain, the profitability goes up. Again, it's considering everything else being constant. We know that profitability is affected by prices, but again, if you get more rainfall in northeastern Iowa, we get the higher profitability, which some people believe we have to irrigate in some of this area, which I'm not sure when it's happened and how, but that's the whole of the story. My last example is focused on remote sensing, and I know many people, how many people do remote sensing here? I know, Kevin, you do. Okay. Of course, remote sensing, it's a big deal for precision agriculture. It's a second eye or third eye, whatever you can call us. There are a lot of different tools, especially for the last couple of years. The drone system, UAV system, is just changing the area. It's a game changer. And of course, we have a lot of different analytical tools. This is one of the examples. We work with one of the company. This company developed this online tool which allows you, or farmers or agronomists, look at different imagery in different times. So this is the NDVI image, July 25th and August 18th. So farmer can compare the difference. And of course, it gives a lot of analytics, a lot of data, so on. But we've been using imagery for many years. And something what we noticed that a lot of time, we have to be cautious and have some kind of normalized and standard data. Most of you are aware that usually remote sensing people use so-called indices. And one of the common indices is called NDVI, which is Normalized Difference Vegetative Index. It allows to using the red and infrared reflectance to judge about biomass size. And these indices should be in specific range. But a couple of years ago, we looked at the bunch of NDVI map created and provided to farmers by commercial providers, and look at these NDVI maps. And what we found out that a lot of these maps don't have scale, like this one. So this is one of the field, just by Collins here, northeast of Des Moines. We have 2 soybean field, 2 corn field, and you can see that there is no scale. Another important feature here that it's supposed to be green color means the high NDVI value, but look at this here. It used to be, I want to jump, green, and then it became red. The question is why? So there are a lot of inconsistency, and that's okay if you use this imagery for scouting or other purposes, but if you want to use this imagery to do spatial temporal analysis, it's a big challenge. So, and again, we extracted some of the reflectance value for these areas in this field, and you can see that this NDVI actually all over the board. It's just the mass. So that's why 3 years ago we decided to start a new project, which we call Imagery Calibration Project, where we established this site just north of Collins. It's a 2 corn, 2 soybean fields. And we work with industry. We fly this field every 2 weeks with different systems, drones, aerial system, fixed wing. Also in 2016, we worked with Iowa State University scientist, Dr. Matt Dar's group. But what's happened that this field got into the pipeline. So we abandoned that field. And we work with the South Illinois University Edgewoodville, Dr. Randy Pearson group and his students, and they're helping us analyzing this data. Essentially, we put these calibration tarps. So these tarps, we know exactly what they reflect. And based on these tarps, we can actually normalize this imagery. And this is an example. We can normalize it or calibrate this imagery, and now you can see that we have the same scale. So now we can compare this imagery from one year to another from different crops. You can notice that this NDVI values actually, they reach the maximum, so they're not very used. But again, I want to check your eyesight, right? Are you OK? So this is an example of calibrated imagery on the left. This is the field from the same field, 2 cornfield, 2 soybean, on different dates, calibrated imagery on the left, and calibrated on the right. And again, calibrated and calibrated. You notice that there is a big difference. Of course, farmers like this because it shows them a lot of variability and can be used a different way. But for us and scientists, we need this, calibrated products. Another thing what we are looking for is to test in different systems. And we usually work with 5, 6 different companies. We are looking for so-called calibration equations. I believe Kevin understands this. So we're trying to correlate the digital number we get from the imagery and then the percent reflectance base which we get from those calibration tarps. And what's happened often that these calibration equations are not linear. So like in this case, it's extremely skewed or not normal. And this is not good because there is no way we could put all of these tarps, they're very expensive, in all of our trials. So we want to put in just in one trial and then use this equation to extrapolate the data to other places, but it's not. The problem is that a lot of time, imagery providers would scale or truncate the data. And also, they don't usually share raw data. And that's a lot of work with industry and actually changing the industry, how industry work with farmers and group like us or scientists like you to develop better system for doing a lot of research and work in this area of imagery and especially with soybean. Another problem, one of the challenge on farm research with soybean is actually machinery and technique. Like in this fellow, he got stuck with this residue. But the challenge with soybean trial is that a lot of time, although the treatments are supposed to go straight, farmers would have it at an angle. And then these data are not much used. So we spend a lot of time working with farmer communicating this, that these trials has to be harvested at exactly direction the treatments are. Of course, a lot of challenges with soybean, but also opportunities. And another challenge is that because of the soybean seeds are less expensive than corn in relative sense, it's very difficult to study and convince farmers to switch to variable rate planting or variable variety planting. Because technology is here. There are a lot of good technology which allow us to plant seeds in different rates on different variety within the field, but because of a challenge and the cost, it's difficult to do. Another challenge is, especially from remote sensing, that soybean biomass often doesn't really correlate with yield. And finally, the big challenge and opportunity for us is that how we can detect disease, weeds, insect in real time and then apply treatments. So it's a lot of work for us, researchers and industry and universities as well. So again, that's where my 3 examples, how we use these precision agriculture technologies in farm research and how this data can be used for science, farmers, and making decisions. Thank you.
Any questions?
Yes, ma'am.
Kind of broader question, a bit unrelated to what you presented, but I'm curious how the farmers who participate in the ISA on-farm research program compare to state averages. summarize the yield for a given year from the farmers who are participating in the program, how does that compare to the state average?
The question was from Matt that how the farmer who participate in our programs, what's the yield level compared with the average statewide yield? It's a good question, but it's difficult to do because the statewide average is just the average. We work with farmers across the state. I think in some years it's high, some years it's lower. Usually it's higher. And the way we do analysis, we clean a lot of bad stuff. So we clean headlands because again, this is research. You have to remove some of the noise. So some of the numbers on these reports are not really comparable with statewide averages. Because again, we clean data, we remove headlines, we remove waterways, because our objective is to determine the effect of the treatments. That's a kind of, in statistics, call it the contrast effect. You remove a lot of stuff, a lot of noise. It's called nuisance parameters, right? So again, it's a good question. Often it's higher, but it's very difficult to compare because the statewide average has a lot of different areas, a lot of different fields and management. Yes?
In talking about noise, do you have a means to correct each farmer is going to make his or her own decision in terms of the variety for planting and planting date and inputs into the system? Can you also take that into consideration when you bring all the data together and trying to get some figures for what's going on? Can you make calculate correction factors or something like that?
Yeah, the question is how we can make adjustment in our analysis for different management, like planted dates, harvesting, hybrids, varieties in our analysis. It's a good question. We are working on this. Of course, you have to understand that the ratio, the signal ratio to noise in both small plots experiments and farm research is very small. That's a problem, especially soybean, because additional bushel of soybean can make farmers use the treatment or not use because the economics, right? So we are developing tools right now, working with agronomy department and other that would allows us to make some of the adjustment for some of these factors. It's difficult to do. In fact, the varieties, genetics, we don't know is how we can make adjustment because so many farmers use different varieties and hybrids and so on. But for planting dates, rainfall, tillage, and some other, yes, we can. We're not sure it's pretty straightforward relationship in effect, but yeah.
All right, let's thank Peter again.
Thank you. Thanks.